So this is Chapter 19 on amines, Part 1. Here are some examples of biologically active amines. They're classified as alkaloids and often are addictive. They're synthesized mostly by plants, and they're used by plants to protect them from being eaten by other insects and animals. Here are several different types of amines shown here, and you can see that many of them have different biological activities. Some are amino acids that are in proteins, others are neurotransmitters, vitamins, etc. So here are some examples. If we look at the classes of amine, you have primary, secondary, tertiary, and quaternary. And the reason why there is a quaternary is because you can have another alkyl group attached to the nitrogen to give it a positive charge, leading it to have a quaternary structure. Primary, it has one alkyl group. Secondary has two. Tertiary has three. And now quaternary, something you now know. In terms of classification, here are examples of primary amines, secondary, as well as tertiary amines. In terms of quaternary amines, they're also known as quaternary ammonium salts. The nitrogen has four different things, or four different alkyl groups attached to it, and bears a positive charge, and also can have a counter ion attached to it. Common names of amines are formed from the names of the alkyl groups bonded to the nitrogen, followed by the suffix amine. So this is two carbons, which will be ethyl, and then followed by amine. This is isopentyl. There are two of them, so this would be diisopentyl amine. This is ethyl, 2 and 1 methyl, so it's diethyl methyl amine. Tert but ammonium chloride, cyclohexyl dimethylamine, benzylamine, and diphenylamine. On a molecule with higher priority functional groups, the amine is named as a substituent. So this would be higher priority. So this would be cyclopentene, and it would be 1, 2, 3 amino cyclopentene, or cyclopent 2-ene 1-amine. This is alpha, beta, gamma amino butyric acid, or 4-amino butanoic acid. These are trans to one another, and it's a cyclohexanol, so it's 3-amino cyclohexanol, and it's trans. And this is a benzoic acid, but para-amino benzoic acid. IUPAC names, the name is based on the longest carbon chain. E of the alkane is replaced with amine. So here it's 4, so it's butane 2-amine. This is still butane, so it's 3-methyl butane 1-amine. This is still butane 2, and it's N-methyl butane 2-amine. And here it's a hex prefix, so it's 1, 2, 3, 4, so it's 2,4-NN tetramethyl hexane 3-amine. In terms of aromatic amines, the amino group is bonded to a benzene ring. The parent compound is then called aniline. So here's aniline. This would be ortho, or 2-aniline, so this would be orthoethyl aniline. This would, at the same position, it's ethyl group, so it's NN diethyl aniline, and this would be 4-methyl aniline. So when naming a cyclic amine, the nitrogen is assigned position number 1. So it's aziridine, as you know, pyrrolidine, and if we're numbering pyrrolidine, if there's a methyl group attached, this would be 1-methyl pyrrolidine. Imidazole, where you're numbering it 1 at the nitrogen bearing the hydrogen, 2, 3, 4, 5 around the ring. Indole, again, nitrogen bearing the hydrogen, 1, 2, 3, 4, 5, 6. Pyridine, if you have a substituent, you want this substituent to be on the lowest carbon around the ring, so this is 2-methylpyridine. Pypyridine's here. Again, the numbering is from 1 around. Pyrimidine, you have 2 of these nitrogens, so any one would be 1, and then it goes 1, 2, 3, and around the ring. Purine is the kind of odd ring numbering terms. You just have to know which nitrogen to number it from. It's the farmost here on the left, and then it goes 1, 2, 3, 4, 5, 6, finishing 1 ring off, and then 7, 8, 9. Structure of amines. Nitrogen is sp3 hybridized with a lone pair of electrons on top, shown here. And because of that lone pair of electrons, the angle is less than the ideal 109.5 in tetrahedral geometry. It's 107 in the case of ammonia. In the case of trimethylamine, it's 108. Amines undergo conversion, especially since it has these lone pairs. So this would be R-ethylmethylamine. Undergoes conversion where it goes to this flat transition state and then flips right over to the S. So because of this lone pair, it undergoes inversion around the nitrogen. Amines that are in the presence of a carbon, but that carbon is chiral, will remain chiral, and so in this case, the nitrogen inversion is not relevant because it doesn't affect this chiral carbon. Quaternary ammonium salts, however, can have chiral nitrogen if these 4 things or substituents are different, and inversion of configuration is not possible because there's no lone pair in these cases. You could also have chiral cyclic amines. Here's an aziridine, which has a specific configuration, and here's the other, the S form. Here, because it's in this constrained ring, it can't flip over, and so the inversion is slow in this chiral cyclic amine, and as a result, you can resolve these 2 enantiomers. In terms of boiling point, NH is less polar than OH. There's an overall dipole moment here, and so weaker hydrogen bonds. So amines will have a lower boiling point than the corresponding alcohol, right? Tertiary amines can't hydrogen bond, so they have lower boiling points than primary and secondary amines. So in terms of hydrogen bonding, here's a tertiary amine, and because it has less possibilities for hydrogen bonding, its boiling point is low. In the case of an ether versus a secondary amine, right, yes, secondary has more sites of hydrogen bond acceptors and donors relative to the tertiary amine, so it has a higher boiling point. However, with respect to ethers, the ether actually has a lower boiling point because it only has donors. In the case of the primary amine, again, it's larger than higher than the secondary amine, however, still lower than an alcohol, as in the previous slide. Small amines, less than 6 carbons, are soluble in water. All amines accept hydrogen bonds from water and alcohol, and branching increases solubilities. Most amines smell like rotting fish, as you can see by the names cadaverine and putrescine. So the lone pair of electrons on nitrogen can accept a proton from an acid. Aqueous solutions are basic to litmus. The ammonia pKb is about 4.74. Alkylamines are usually stronger bases than ammonia. Increasing the number of alkyl groups decrease the solvation of ions, so secondary and tertiary amines are similar to primary amines in basicity. If we look at the reactivity, of amines, you have your nucleophile from those pair of electrons from your nitrogen attack, kick off to generate this new nitrogen-carbon bond. If we look at the amine as a proton base, it can pluck off a proton, kick off, generating the protonated version. Base dissociation constants. We've talked about this as a pKb. Ammonia has a pKb of about 4.7, so they're strongly basic, and as such can abstract protons from water, giving ammonium ion and hydroxide ion, as shown here. And the equilibrium constant for this reaction is the base dissociation constant for amine, symbolized by this Kb. An important thing to note is that the pK of a quaternary ammonium salt, or shown here, is the pH at which half the molecules are protonated. At lower or more acidic pH, the amine is mostly protonated. At higher or more basic pH, the amine is mostly deprotonated. If we look at the energy diagram, you have amine with water plucking off that proton from water to generate the ammonium ion and hydroxide. And so it starts at a lower energy going to a higher energy. The alkyl groups, if you add alkyl groups, stabilize the ammonium ion, making the amine a stronger base. So if we look at, for example, pKb from just ammonia, then with an alkyl group, this is a primary, we can see that the pKb goes from 4.7 to 3.4. So alkyl groups make the nitrogen base a stronger base than ammonia. In terms of aniline, you have the ring, the electrons on the nitrogen participating in the p orbitals of the ring. As a result, this is more stable than when it's protonated. That is eliminated, and there's no overlap possible. As a result, if we look at the energy diagram, the aromatic amine is much lower in energy than the aliphatic amine. And so it gets to the same point. However, it needs to have more energy, activation energy, in order to get across. Protonation of pyrrole. Here's pyrrole, aromatic in the presence of water, and then it becomes non-aromatic when you protonate. So protonation on the nitrogen ring is very unfavorable, and the pyrrole is a very weak base. And pyridine is less basic than aliphatic amines, right? But it's more basic than pyrroles, because this nitrogen electrons does not participate in the pi system. As a result, it doesn't lose its aromaticity upon protonation. So in general, aromatic amines are less basic than aliphatic amines. This is true both when the nitrogen atom is part of the aromatic system, as in pyridine, and when the nitrogen is bonded to the aromatic ring, as in aniline. So here's your amine, and the free amine is water insoluble. If you protonate, it becomes the amine salt, and it becomes water soluble. If you deprotonate, it becomes water insoluble. So once you protonate, it's in an ionic solid with high melting points. It becomes soluble in water, and the fish odor. So then you can use that property to purify amines. So you can have the amine in the ether phase, and then you have your water phase. You can then remove the water phase, right? And then add dilute HCl, which will protonate it, so then it'll go into the water phase, and then whatever the rest in the organic solvent. Then you can remove the organic solvent phase, add sodium hydroxide, and then as a result it becomes an amine again and soluble in the organic phase, and then you can remove the water phase and have your amine. So you can do the same thing in this process where you have your mixture of your amine and impurities. Shake with ether and water. Ether, you'll have the amine and the organic impurities. Inorganic impurities and salts will be taken away. If you shake this with proton or dilute acid and water, now it's going into the salt. Organic impurities you can discard. Then you add base, and then it becomes the amine again in the ether, and then the impurities can be eliminated. You can react amines with ketones or aldehydes shown here to generate the carbonylamine and then the derivative. And depending on which amine you use, if Y is an H or an alkyl chain, it gives you an imine. If it's an OH, it's an oxime. If it's an NHR, it's a hydrazone shown here. Aromatic substitutions of arylamines. NH2 is a strong activator, so it's a ortho and para director. Multiple substitutions become a problem because it's a strong activator. Protonation of the amine under acidic conditions converts the group into a strong deactivator, or NH3+. So here is aniline. If you add excess Br2 in sodium bicarbonate, you get multiple substitutions on the ortho and para positions. Here, excess Cl, again, multiple substitutions. The reason why you have ortho and para substitution has to do with the resonance structure and the electrons participating in the ring system when it's ortho and para. It's not possible to do in the meta substitution, and as a result, you have this preference. And we've done this in the previous chapter, so I won't be doing this in detail here. So if you protonate, you can protonate the aniline with just strong acid, and then it becomes deactivated, and so it won't further react with other electrophilic aromatic substitutions in the ortho and para position. So as a result, it would suitably deactivate and then just allow for meta substitutions to occur. So if that happens, when you add acidic conditions, like in the nitration conditions, what will happen is it'll just protonate, and then that's it. You won't have the reaction occurring, and then you might have oxidation of the NH2 group, etc., etc. If we look at aromatic substitutions of pyridines, they're strongly deactivated towards electrophilic attack by this electronegative nitrogen atom. As a result, it then can only allow for meta substitution, and electrons on the nitrogen may react also with the electrophile. In this case, if you're doing sulfation, it also reacts over here to form the protonated version of the pyridine. In terms of electrophilic aromatic substitution, it's going to prefer the meta. Once it has the meta, you can have the electrons move over here again, and again over here, and then you have elimination to generate the 3-nitropyridine. If you try to do attack on the ortho or para, what would happen is you'd have positive charge retaining on the nitrogen, and that would be unfavorable because it's not an octet here, and so this really doesn't happen. So in terms of nucleophilic substitution, you can have your electrons go, kick off the electrons to the nitrogen, and the negative charge will reside on the nitrogen, and that's favorable, right? You have an octet, this is favorable. As a result, ortho or even para-position substitution is actually something that happens. And then you can have electrons from this ring move around as I'm showing here. And then you can have elimination to generate your product. If you tried a nucleophilic attack on the 3 position, this is what would happen. Electrons come in, kick off. Here, here, and here, you don't have any delocalization of the negative charge on the nitrogen at all in such case. As a result, substitution on the 3 position isn't observed. Alkylation of amines by alkyl halides. So here you have amine reacting with just another quaternary amine, and you can have exchange occurring in which your electrons attack. This is a good leaving group. Sorry, let me draw this out. So you generate your secondary amine. Now this can attack again, SN2, generating a salt of a tertiary amine. So it proceeds by an SN2 mechanism. Secondary alkyl halides will give elimination products. Multiple alkylations is a major problem, and complex mixtures are obtained. You can do exhaustive alkylation by adding methyl iodide, and then this will react, right, with this carbon until you exhaustively methylate under sodium bicarbonate conditions to neutralize that acid that is being formed. So you can use an excess of ammonia and react with alkyl halides to form primary ammonium salts, and excess ammonia is allowed to evaporate after the reaction. So here's your product. So here we're going to end here for part 1 and continue on in another lecture.